Today we're going to take a look at 5.2 bisectors in triangles. So as we go through this lesson, there is a lot of vocabulary. They kind of listed over here to the side. What I would highly recommend you do is if you take notes, if you have like a composition book or like a notebook that you use to take notes in and do your problems in, definitely have that out as we go through. I'm going to highlight all these vocab words. But if you don't have like a notebook that you take notes in, grab some paper, some blank computer paper, some blank line paper, and copy these down. Or, at the very least, make sure you're following along so you know where to go back and reference these vocab words. Geometry in its own sense is kind of its own branch of mathematics. It's kind of, it teaches you a lot of things. But it's only really useful. Well, I shouldn't say that. It's only super prevalent in geometry. You won't see a lot of this information as you continue to go through the algebra-based courses like Algebra 2, Pre-Calculus, Calculus, things like that. So anyways, long story short, just make sure you're copying down notes or emphasizing writing down these vocab words. Super important. So the first thing, looks like they're kicking it off, which I haven't really seen before. Let me make a little bit of room on my desk here. They're kind of kicking off the lesson with a theorem, right? Like a property, like a rule that's happening here. So they're calling it the concurrency, which is a vocab word if something is concurrent. Concurrency of perpendicular bisectors. Perpendicular bisectors are not new to you. They're old news, but the concurrency part of it is something that's new. So the perpendicular bisector, and just to be clear what a perpendicular bisector is if I have a line segment, that could be the side of a triangle, it could just be any line segment out there in the world. We'll call it AB. So this is line segment AB. A perpendicular bisector has two parts to it. So perpendicular bisector. Okay, perpendicular bisector. Perpendicular means that it's going to meet at that line at a right angle. Okay, so perpendicular means it goes straight up from that line. Bisector means it's going to cut that line length in half perfectly. Again, we skipped constructions where you take a compass and a straight edge and you create the perpendicular bisector. So I'm not really focusing on how to create that, just the idea of what it does. So if I create a perpendicular bisector, it's going to cut this line perfectly in half. So imagine that point is perfectly in between those 2 points. So this distance between A and C, that's the exact same distance between B and C. And then the bisector, or the perpendicular part, that's the line that goes straight off of that line AB. So that's my perpendicular bisector. It lands right in between those 2 points. So it creates two line segments that are the exact same length, and it's straight off of that line. It goes off of it at a 90-degree angle. Okay, so the perpendicular bisectors of the sides, so they're just looking at the sides of the triangle, are concurrent at a point. And all that means is they meet at a point equidistant. So that's the same distance from the vertices. So the vertices are like right here. Basically the points where the two sides meet. So B is a vertice, C is a vertice, A is a vertice. Lots of vocab just in that one little statement right there. So the perpendicular bisector of the sides of a triangle are concurrent at a point equidistant from the vertices. So what that's saying is here's all my perpendicular bisectors, right? They come straight off that line, right in the middle, right in the middle. So the point where they're calling point P, that's that concurrency point that they're referencing to. And the important part of that is right here. That point is equidistant from the vertices. That means it's the same distance. So if you walked from A to P, you would walk the same distance as somebody that walked from C to P and B to P. So when that happens, that's the information you're pulling from it. Those perpendicular bisectors meet at a point. That point P is the exact same distance between all three vertices. All right. So hopefully you're like, man, Chapman, you weren't lying. That is a lot of vocab, right? Example 1, prove. Again, we're not doing proofs. We're not walking through it, but I'm still going to walk you through this problem though, because there's some vocab in it and I just want to explain what's happening here. So when 3 or more lines intersect at one single point, the lines are called concurrent. So again, concurrent is just a fancy word of saying where 3 or more lines meet. But when you go through the vocab, when I continue to go through the lesson, I'm not just going to reference where the lines meet. I'm going to say where they're concurrent. So make sure you know what that means. The point where the lines intersect is called the point of concurrency. Okay, so when the 3 lines intersect at one point, those lines are concurrent, and then where they intersect is called the point of concurrency. So how do you prove it? Well, again, we're not going to prove it, but take a look at what I want to walk you through this picture that they have going on here. Maybe this, well, we'll start off up here. So you've got the 3 sides of the triangle, and what they're trying to show you here is that dotted line. That's that perpendicular bisector that we talked about a minute ago. You can see it's perpendicular because it's coming straight off of that side, BC. It's coming straight off of it because of that 90-degree angle. And you can see it's a bisector because look, it cut that side BC into 2 equal parts. So I know that this dotted line right here, that's a perpendicular bisector. Same thing with this dotted line for the line AC. Same thing with this dotted line for the line AB. So they're just emphasizing that those are perpendicular bisectors. Well, here you can see that they kind of extended those bisectors. Notice they only kind of drew it to where you didn't have the middle part, just because they want to emphasize that. Here, they kind of extended those lines, those same lines. So the perpendicular bisector called R and called Q. Notice that the perpendicular bisector S is not there right now. Right? Because what they're doing is they're saying those 2 perpendicular bisectors, they're already meeting at point P. Here's where they added line L, right? That perpendicular, I'm sorry, line S. That's what they called it up here. Here they added perpendicular bisector S. They didn't have it over here. But notice when they add that 3rd side, it still goes through point P. That doesn't change. So really, if you have 2 of the 3 perpendicular bisectors, it's going to give you point P. You can add the 3rd perpendicular bisector. It's still going to go through point P because they all 3 have to go through the same point. And this is just emphasizing what that theorem we just looked at the beginning is talking about. Those perpendicular bisectors meet at a point. That point is the same distance away from all 3 vertices. Okay. Let's take a look at example 2. So this kind of goes over onto the next page, but we'll walk through it starting off. How can you construct a circle that contains the 3 vertices of a given triangle? Well, I think my problem when I was going through geometry was I was like, we'll just draw a circle around it, right? I mean, that's not hard. But you have to use like the properties that allow you to draw the circle. So that's where they're getting at. So the circle that contains all 3 vertices of a triangle is the circumscribed circle of the triangle. Circumscribed. So let me reword that because that's really important that you know what this vocab means. I'm not going to reword it. I'm just going to reread it. The circle, so that's this dotted line that contains, so it's basically including all 3 vertices of this triangle. So notice this circle basically cuts and touches that vertice, comes around and touches that vertice, comes around and touches that vertice. That's called vertices of a triangle is the circumscribed circle of the triangle. So they call that a circumscribed circle. Here's some notes, right? All points on a circle are equidistant from the center of the circle. The vertices of the triangle must be equidistant from the center of the circle. And that's just emphasizing the same thing. Any point on this circle, any point on this dotted line, right? It's going to be, if you find the center of that circle, it's going to be the same distance, right? Because a circle is perfectly round. If the distance from the top of the circle to the center is, I don't know, let's just call it 4, then the distance from the left side to the center has to be 4, from right here to the center has to be 4. All of those distances are the same distance. Well, look what's lying on that circle, all 3 vertices. That's what they're emphasizing here. Since all 3 vertices are on that circle, right, on the outside of the circle, then the distance between each vertice and the center of the circle has to also be the same. So I think they're wrapping it up down here. By the concurrency, I always want to say congruency, by the concurrency of perpendicular bisectors theorem, the perpendicular bisectors intersect at a point that is equidistant from the vertices. Okay, and that's kind of what we were emphasizing in example 1. This is still the same example, example 2. So the point of concurrency, so that's the point where they all meet, right? All 3 lines or 3 or more lines meet. I think they're sticking with 3 lines because we're dealing with triangles. So the point of concurrency of the perpendicular bisectors of a triangle is the circumcenter. Okay, so the point where they all meet, that's called the circumcenter. So the circumcenter is the center of the circumscribed circle of the triangle. Try to say that 5 times fast, right? But let me emphasize what they're talking about. Just like we said back down here, right? That if we draw this circumscribed circle, then any point on that circle is the same distance from the center. Well, the 3 vertices are on this circle. So from the vertices, from those 3 vertices to the center of the circle has to be the same distance. That's exactly what they're kind of emphasizing up here. The point of concurrency of the perpendicular bisectors of a triangle is the circumcenter. So that's the vocab word. And this is where they're kind of emphasizing what it means. So the circumcenter, that vocab word, is the center of the circumscribed circle of the triangle. So the circumcenter, here's that dotted circle. If this is my circumcenter, then that has to be not only the center of the triangle, but also the center of the circle, right? That's all that's saying. Lots of vocab words, lots of words that kind of sound similar. So that's why I'm just really emphasizing the idea of these vocab words. Example 3. Use a circumcenter. So you might be thinking, why does all this stuff matter, right? There's a lot of times in math where you learn something and, you know, honestly, unless you teach math, you may not use that idea or that concept. Here's what you can do, right? We're talking about circumscribed circles, circumcenters, all that kind of stuff. Let's look at how this can be applied. So a city manager wants to place a new emergency siren so that it's the same distance from the school, hospital, and recreation center, right? So we have these 3, you know, places, and we want to place a siren. You know, if there's an earthquake or a tornado or whatever, we want to place a siren around those 3 places to where it's the same distance from each place. So that way everybody can hear the siren as best as possible. Where should the emergency siren be placed? So they're giving you some steps here. Let me walk you through it. So they have this kind of map, right? And they're saying the hospital is here, the school is here, the rec center is here. So what do you know? When you connect all 3 of those places, it forms a triangle, right? It forms a triangle. Well, kind of like we talked about, we can do some stuff to basically find a place. They're calling this place E, where this place is going to be the same distance from all 3 of these places, the hospital, the rec center, and the school. Okay, so here's how we do it. They're labeling, they're setting this up. So label S for school, H for hospital, R for rec center, and connect the points to make a triangle. We already talked about that. Step 2, construct the perpendicular bisectors. That's the main go-to thing that you're going to do. Again, you're not going to actually construct them, but when you look at information, that's what you're going to have to look for to pull that information out. So construct the perpendicular bisector of 2 of the sides. You might be thinking to yourself, well, why 2? Why not 3? Remember what we talked about back here in example 1. If you do perpendicular bisectors of 2 of the sides, it's going to give you that point. If you want to verify it to make sure you didn't screw up, go ahead and make that third perpendicular bisector, but it should go through the same exact point. So that's why they're emphasizing here, you only need 2 perpendicular bisectors. Let's see what they used. It looks like they used the perpendicular bisector of HS and of RS. Now, correct me if I'm wrong, but I don't think I am. If you create a perpendicular bisector of HR, that's still going to go straight through that point E. Okay. But all you need is 2 of the 3 sides. So that point where those 2 perpendicular bisectors meet, they're calling that point E, which is essentially the point where they're going to put that emergency siren. Okay. So that point where those 2 perpendicular bisectors meet, that distance between E and H is the same distance between E and R, which is the same distance between E and S. All right. Let's take a look at what they're saying up here. Another kind of special segment in a triangle is the angle bisector. So we talked about the perpendicular bisector, which is basically taking any side of the triangle and creating a perpendicular bisector where it cuts that side in half perfectly, and then it goes straight up off of that side. Okay, so that's one thing that we've talked about. Here's the second one, an angle bisector. Kind of the same thing, but instead of sides, you're dealing with angles. So let me emphasize this on a piece of paper. So this is the perpendicular bisector. This is the angle bisector. So let's just draw a random angle. It doesn't matter what the angle is, right? But we have an angle. This angle bisector is going to essentially, and again, it's a construction. So if we had a compass and a straight edge, you can physically construct this angle bisector. It's not just a random line, it's a specific line. And when you construct it, it's going to come straight out of that angle, and it's going to split this original angle in half perfectly. So let's say that this entire angle, what we started with, let's say that was, I don't know, 50 degrees, okay? That's the angle that we started with. That's this angle right here, okay? So the red is 50 degrees. Then once we create this perpendicular this angle bisector, it's gonna cut that angle in half perfectly. Got some Christmas colors going on here, which means that each of those smaller angles are 25 degrees. Okay, that's the big idea. And again, an angle bisector is not just drawn randomly like I did. If I had a compass, I'd show you, but you could actually construct the angle bisector. You'd get 2 points, you'd connect the dots, and it would go straight through that angle and cut that in half perfectly. Okay. So I'm assuming that's what they're going to go into. Let's keep reading. Like the perpendicular bisectors of a triangle, the angle bisectors of a triangle also have a point of concurrency. So let's look right here in this picture, and then we'll talk about what the theorem says. Here's a triangle. What you'll notice here is that instead of perpendicular bisectors, you have angle bisectors. They're coming straight out of these vertices, X, Y, and Z. They're coming straight out of those vertices, and they're meeting at a concurrent point, right? A point of concurrency. So it's taking that bigger angle, cutting it in half perfectly, taking angle Z, cutting it in half perfectly, and then they meet at this point of concurrency. So both perpendicular bisectors and angle bisectors, both of them have a point of concurrency. In this picture, it's point Q. So the theorem, again, just kind of a rule in math, concurrency of angle bisectors. The angle bisectors of the angles of a triangle are concurrent at a point equidistant from the sides of a triangle. So what they're saying here is when you create these angle bisectors, you get this point of concurrency, what they're labeling Q, okay? This point of concurrency is equidistant, so it's the same distance from the sides of the triangle. So between Q and we'll call it YZ, between Q and XY, between Q and XZ, it's the same distance, okay? So keep that in mind. Example 4, investigate inscribed circles, okay? So how can you construct a circle that intersects each side of a given triangle at exactly 1 point? Now, this is not the same thing that we already talked about. Let me go back to that. Right here, example 2. Investigate circumscribed circles. Notice here in this situation, that circle intersects all the vertices of the triangle. It's on the outside of it. So the entire triangle is on the inside, right? Now take a look at what we're looking at now with example 4. Now the circle is not on the outside intersecting all the vertices. The circle is on the inside. And the point of it is that the circle is touching all 3 sides of the triangle. So the way I remember this is, well, it's hard for me to remember circumscribed, right? I mean, I've been doing that for a long time, so I know what it means. It's the circle on the outside touching all the vertices. But the defining one is the inscribed circle. So circumscribed circle goes on the outside. Inscribed circle goes on the inside of the triangle. So hopefully that makes sense to you. Hopefully that helps you. That's something you could write down in your notes. Inscribed circles go on the inside of the triangle. Circumscribed circles go on the outside. They just touch the vertices. Okay. A lot of text here. So let's hit on these vocab words, and then I'll just kind of summarize what example 4 is saying. So how can you construct a circle that intersects each side of a given triangle at exactly 1 point? So you're touching 1 point on that side, 1 point on that side, 1 point on that side. So let's look at this vocab word. The circle that intersects each side of a triangle at exactly 1 point and has no points outside of the triangle. So what they're saying is that this circle touches each side of that triangle at 1 point, but it doesn't exist outside of that triangle. They call that the inscribed circle. So it's inside the triangle. And then a couple of hints for you there so you could read through that. Oh, look at this study tip. These are good. If you're not reading through these, take a look at these. Make sure you read those. The parts of the word in center can help you remember what it means. It is in the center of the circle. That means inside of the triangle. It is the center of the circle that is inside the triangle. So it kind of gives you just little hints, as you go through there. So by the concurrency of angle bisectors theorem, right? We just took a look at that at the top of this page. The angle bisectors of a triangle intersect at a point that is equidistant from the sides of the triangle. We've already talked about that. The point of concurrency, that's that point where all 3 of those angle bisectors meet, of the angle bisectors of a triangle, is called the incenter. So let me go back up here and look. In this situation that we have right here, we have a triangle, and these red lines are angle bisectors. They cut those angles, right, those vertices perfectly in half, and they met right here, and that's called that point of concurrency, right, where those three lines meet. But what that was just talking about down there, that incenter is referring to that point right there. So the point of concurrency of the angle bisectors of a triangle is the incenter. That point right there, point Q, is called the incenter. So the incenter is the center of the inscribed circle of the triangle. Okay, the center is the inside circle of the triangle. And here's how they're walking you through it right here. So they got a triangle. It looks like they did 2 of the 3 angle bisectors. Remember, just like with the perpendicular bisectors, you only need 2. Same thing with the angle bisectors. If you create an angle bisector here, it's going to go through that same exact point. So you only need 2. So there's my point of concurrency, also called the incenter. Okay. So here's that same triangle. This red line, that's the perpendicular bisector, that's basically coming. I'm sorry, I misspoke. It's not the perpendicular bisector. It's a perpendicular line that's coming straight off of that side of the triangle, and then it's hitting that incenter. Okay. It's coming straight off of that side of the triangle, touching that incenter. So this incenter is right there. The radius of the inscribed circle is that distance between the incenter and then that perpendicular line to the side. So whatever that size is, or that distance is, what we do if we were in class is we take a compass, open it up, touch one side to the incenter, touch one side to that point right there, and then we trace a circle in the middle of it. Because this distance right there between the incenter and that side, that's going to be the same distance between the incenter and this side, the same distance between the incenter and this side. So that would form that circle. Lots of vocab words. That might be, if you're kind of feeling a little lost right now, just slow down, kind of refer, either read these vocab words that are in here, maybe Google them. I think there's a website called Math is Fun, and you can Google it on Math is Fun. You can go to mathisfun.com, Google the word inscribed, Google the word incenter, and inside that website, and it'll really maybe simplify that for you. It'll explain it in a different way that hopefully makes sense. Okay. So example 5, identify and use the incenter of a triangle. Okay, the incenter of a triangle. Just keep in mind that incenter, and you can look back on page 212, that incenter is basically just the center of the inscribed circle. So if I drew a circle that touched all 3 sides there, the incenter is that middle, the center of that circle, okay? So let's look at what they're giving us here. If QP is this expression, right? RP is this expression. What is the radius of the inscribed circle of JKL? So if you look at their picture here, they're saying QP, that distance between the incenter, which is point P, and then that Q, the point on the side, JK, which is Q, that distance is 3 times x plus 1. RP, which should be the exact same distance, right? If P is the incenter, then the distance between P and each side is the same, okay? So all I'm gonna do, let me get a piece of paper, is set those things equal to each other. So 3 times x plus 1 equals 5x minus 3. So I'll do some algebra, distribute that 3. So I'll have 3x plus 3 equals 5x minus 3, and then just solve for x. I like to keep my variables positive. You could have subtracted 5x from both sides, but I just like to keep the variables positive. So I'll have 3 equals 2x minus 3. I'll add 3 to both sides, so I have 6 equals 2x. Divide both sides by 2, and I have x equals 3. So just some algebra. Again, there's multiple, if you wanted to add, subtract 5x from both sides, you could have done different steps, but we should get down to the same answer, x equals 3. So let's solve for x. That was their first step. Yep, I got 3. And then what are they looking for? What is the radius? So I can just plug that value into either of those expressions. It's completely up to you. If I plug in x is 3 here, or if I plug in x is 3 here, it's going to give me the same number. So I will go ahead and plug it into QP. So 3 times x plus 1, that's my radius of my circle. I know x is 3. So I'll plug in 3 for x. 3 plus 1 is 4. 3 times 4 is 12. So I know the radius of this circle is 12. Let's verify that. Yep, perfect. All right. Oh, and that's it. So concept summary on page 214. This is just emphasizing the 2 main ideas about perpendicular bisectors and angle bisectors. When you create perpendicular bisectors, what it gives you versus when you create angle bisectors, what it gives you. Make sure you understand the vocab there. It's saying perpendicular bisectors intersect at the circumcenter, right? That's the point where they're all 3 crossing. And then the circumcenter is equidistant from all vertices. So the distance between P and B, P and A, P and C is exactly the same, okay? And this is almost the opposite. So I have angle bisectors. The three angle bisectors meet at point N, and this is called the incenter. And what that's saying is the distance between the incenter and each side is the same. So I could draw a circle there. The distance between N and AB is the same distance between N and BC, which is the same distance between N and AC. All right, I switched over to the practice problems. I was going to switch it up in 2 videos, but there's not a lot of problems, 15 through 22, so just a handful. We'll go ahead and knock it out on the same video. Practice problems. So let's take a look. The perpendicular bisectors of triangle JKL are line PT, line QT, and line RT. And you could see that here. PT, QT, and RT. Name 3 isosceles triangles. So again, really heavy on vocab. An isosceles triangle, if you don't remember, was a triangle like this, where it had some properties to it. The 2 side lengths are the same, and the 2 base angles are the same. So that's an isosceles triangle. With number 15, just remember that this point, point T, that's basically the same distance between each angle, right? So point T, the distance between T and J is the same, T and K is the same, T and L is the same. So perpendicular bisectors give you the same distance between that point of concurrency and the angles. And then the other way around, angle bisectors give you a point of equidistance between that point of concurrency and the sides, okay? So if that's the case, then it looks like this triangle from T to J and from T to L. So it's this triangle down here, not just one of these little ones, this entire one. If those 2 sides are the same length, then that has to be an isosceles triangle. So we'll call it JTL. So triangle JTL is one of them. They want 3. So again, from that point of concurrency to L, from the point of concurrency to K, those have to be the same distance. So this gives me another one. We'll call that, I don't know, LTK. And then the last one, from T to K, from T to J, those have to be the same distance. So that little tiny triangle at the top, that has to be an isosceles triangle as well. So we'll call that KQJ. All right. So again, vocab, right? Make sure you know what an isosceles triangle is. Make sure you know the properties of it. Make sure you know what an equilateral triangle is, things like that. Use the diagram below for 16 through 18. Points D, E, and F are the midpoints of the sides. So they're just giving you some specific information that's really important. So D, E, and F are the midpoints of that side. So that's just telling you that this line right here, for example, line ET, line ET is not only perpendicular because of that 90-degree angle. If E is a midpoint, that means it's a perpendicular bisector, okay? It cut that line, CB, it cut that line perfectly in half. So that line ET is a perpendicular bisector. Same thing with the other ones. FT is a perpendicular bisector of AC, and then TD is the perpendicular bisector of AB. All right. Which point is the center of a circle that contains A, B, and C? So A, B, and C, those are my 3 points. So which point is going to be the center of the circle that contains those 3 points? So in this picture, just keep in mind that the perpendicular bisectors, the thing that they emphasized up here that I just pointed out, when you create perpendicular bisectors and they meet at that point of concurrency, which is they're calling it point T right there, that point of concurrency would be the center of that circle. So you just need 2, but in this case, they gave you all 3, ET, FT, and DT. They meet at point T, that's the point of concurrency. That's the center of the circle. So for 16, I would just say, which point? You just say point T. 17, which point is the center of a circle that intersects each side, right? That intersects each side of triangle ABC. That's important, the each side of triangle ABC at exactly 1 point, okay? Now we're moved to the angle bisectors. So the point of concurrency when you have perpendicular bisectors, that's the center of the circle, but the angle bisectors will give you the center of the circle that's inscribed in that triangle. So step 17 is focusing on the angle bisectors. You can see here each angle, each vertice is cut and they're meeting at point P. So for 17, point P would be the center of a circle that intersects each side. Looks like 18, we're using the same diagram, so let's read through it. The perpendicular bisector of AB, let's see what they're talking about here. That's right here. That's the line DT. That's the perpendicular bisector is M, and the perpendicular bisector of BC is N. They don't have M and N up here, so I might have to sketch this, but we'll see what it's asking for. So AB, that's M. So line DT, they're calling that M. The perpendicular line BC, so that's ET. They're calling that line N. Lines M and N intersect at T. They do. So DT and ET, they're calling that line M and line N. They intersect at point T. If TA is 8.2, what is TC? So if TA from that point of concurrency from T to A, if that distance is 8.2, what is T to C? Again, the point of concurrency to the other vertice. Just keep in mind when you're dealing with both of these instances, angle bisectors, perpendicular bisectors, those point of concurrencies, when they all meet at point T, they're giving you the same distance between T to A, T to B, and T to C, right? All the distances are the same. It's basically the center, right? So in this case, they're saying if TA is 8.2, if that distance between that point of concurrency and A is 8.2, well, then the distance between that point of concurrency and B has to be 8.2, and the distance between that point of concurrency and C has to be 8.2. All the distances have to be the same. All right. Let's go down to find the values. Let me get this on. There we go. So for this example, looks like we're using this one right here. For 19, find the value of EG. So a lot of busyness happening here. Try to ignore the stuff you don't need. But what they're looking for is the distance between E and G right here, okay? The first thing I really want to emphasize here is they're giving you information in red, and they're not just giving you it, well, maybe they might be giving some of it just to throw you off or maybe to use for the other problem, but they're giving that to you for a purpose. They're telling you that this line EG, notice that it comes off at a right angle. So I know that that's perpendicular to that line BC. It's not a bisector, right? It's not showing that the sides are cut in half perfectly. Let me show you an example of that. Ooh. Oh, right here. Right? This is a perpendicular bisector. I know it's a perpendicular because of that 90-degree angle. And I know it's a bisector because they're cutting both of those sides in half and they're labeling them that they're the same. Okay? That's not happening with number 19. Okay? All we can see is that it's perpendicular. There's no label showing that the side lengths are the same amount. Then it's showing you from D to G, that's also a perpendicular line. From F to G, that's a perpendicular line. So some information there. And then it looks like they have some angle bisectors as well from angle B and angle A. So that point of concurrency G right there in the middle, that's what all that information is telling you. All of those two angle bisectors are creating that point of concurrency G, and then it's showing you that the distance between G to E has to be the same distance between G to D, and it has to be the same distance between G to F. So this is focusing, number 19 is focusing on angle bisectors. The point of concurrency is G, and the distance between G and each side is the same. So they're giving you one of the side lengths between G and D is 9. So I know that G and E, or E and G, whatever you want to call it, has to also be 9. They have to be the same distance. Okay. G and F is right here. So again, if G and E and G and D and G and F all are the same distance, then G and F also has to be 9. All right, I was looking at the next one, and you're finding distances and calculating things. So I wanted to take a second to go ahead and draw that out, because I feel like it makes a lot more sense when I can write on the paper. For me, maybe not for you, but for me it does. So we're gonna go ahead and label all this stuff. So if XY is 24, so let's go ahead and look at this, XY, so that's the entire distance from X to Y, that's 24. Well, it looks like this was a perpendicular bisector. I know my drawing sucks, right? If you look at this, that looks a lot better. But that's why I'm emphasizing it's a perpendicular bisector, because the two sides were cut in half. They have 3 tick marks. This has 3 tick marks. So that means that they're equal length, and then they come off at a 90-degree angle. So if that's the case, if the whole side was 24, that means this side length was 12 and that side length was 12. They have to be equal. XZ is 22. XZ, that's the bottom. So the entire thing is 22. So that means that that's an 11, that's an 11. JQ is 5. JQ, so that's this piece right here. They're calling that 5. Okay. Find the values, round to the nearest tenth. So find the values. Number 21, the radius of the circumscribed circle of triangle XYZ. For this one, you really have to be comfortable with what they've talked about so far in this section, and a little bit more information as well, okay? I'm going to go ahead and throw this on there. So they want the radius of the circumscribed circle, okay? Well, first we need to know what a circumscribed circle is, right? So a circumscribed circle is where I have something like a triangle, and then that triangle, right? I've got a circle, and again, my drawing sucks, but you get the point. Circumscribed circle means that every point on that circle is the same distance away from the middle, the center of it, and that this triangle, all 3 vertices lie on that circumference of the circle. Okay, so that's a circumscribed circle. So what I'm really trying to find here is the distance. Oh man, I hate screwing up my drawing, but I'm gonna have to do it. And my circle is gonna suck just because my drawing sucks. You know, imagine there's a circle here like this. Again, I know it's not a circle. It's because of my drawing. That's why it's not very good. But again, this is the circumscribed circle. So what I need is this distance. I already know that that's the center, right? Because all 3 of these are perpendicular bisectors. So I already know that Q is the center of my circle. I just need to know how far it is from the center to the edge of my circle. I'm not given any information, right? I don't know the distance between the center and Y, the center and Z, the center and X. But I do have some given information. And I think what I'm looking for is this distance right there. Why did I choose that distance? Well, look, what are we given? Hopefully you're thinking Pythagorean theorem, right? We've got a right triangle. If you look at this triangle right here, it's a right triangle. We've got both the base and the side length. We just have to come up with the hypotenuse, right? So given that information, that's where I went. I guess you could have gone with this triangle right here from Q to X and done that there, because you'd still have the same base and the same side. It doesn't really matter, okay? So that's kind of where my thought process is gonna go here. Remember, Pythagorean theorem you can use with any right triangle. And it's basically what it provides you is the missing piece, the missing information from that triangle. And in this case, my missing information is my hypotenuse. That's what I'm trying to find. So I've got the base, which is 5, and that's going to be 5 squared. Just in case people don't know, the Pythagorean theorem is a squared plus b squared equals c squared. A and B, it doesn't matter. I could use 5 squared plus 12 squared, or I could use 12 squared plus 5 squared. It's the same. C, that's the one that matters. C has to be your hypotenuse. Okay, that's really important. So I'll start off with 5 squared plus 12 squared equals c squared. And let's see if I can do this in my head. 5 squared is 25. 12 squared is 144. 25 plus 144 is 169. And then if I square root both sides, 13. 130. Yeah, 13. So it's going to be positive and negative 13 will be the value for C. Well, remember, anytime you square root a number, it's always the positive and negative version, because 2 times 2 is 4 and negative 2 times negative 2 is 4. So you always want to include the positive and negative versions. But in this case, I think they're talking about the distance, right? The distance from the center of my circle to the edge. So distance is always positive. You can't walk negative 3 feet. So in this case, I'm going to say that my distance, do they label it something? The radius, that's all they're wanting. So the radius of this circle, which again, that is the radius from the center to the edge. So I'll call that QY is 13, right? That's my radius. Again, I'm not using negative 13 because there's no such thing as a negative distance. QK, hopefully we kind of figured out some of this. Let's look. QK, right? So those two, that distance right there. Well, keep in mind, right? Don't forget about these properties when you're using angle bisectors and perpendicular bisectors. You've got to keep those ideas in your head, keep them on a notepad, or just remember to always go back and review this material. I think with this one, we're actually looking for, I'm going to highlight it, QK, which is that one right there. This is the in-center, that Q, right? That point Q, the point of concurrency. So it's the distance. It's not saying that the distance between L and Q, J and Q and K are the same. So just because J and Q, the distance is 5, that doesn't mean Q and K is 5, okay? But what that does is it gives us enough information to do something like, which one do I want to draw? Oh, we'll just do this. So I'm going to highlight my triangle that I'm looking at. Okay. We know that the distance from that point of concurrency to the edge of the circle, we just solved it. What did we say? 13. So now we're just missing that piece down there, QK. So we'll do the same thing. So this is number 22. Oh, I want to kind of keep this on my page here. So we'll do this off to the side a little bit. Again, we're dealing with a right triangle. This is coming straight off of that side at a right angle, so we can use Pythagorean theorem again. We don't have the base, we do have the side, and we do have the hypotenuse. So we're just missing one piece of information, so we can do this. So we'll say a squared plus 11 squared, because that's our side length, equals 13 squared, because that's our hypotenuse. 13 squared is 169. 11 squared is 121. Man, I hope I'm not screwing that up. So now if I have, I don't know why I wrote that, a squared plus 121 equals 169. So I can subtract 121 from both sides. I get a squared equals 48. Is that right? 48, yep. A squared equals 48. Now I can square root both sides. The square root of 48, I have no clue. It's going to be 6 point something. Get my calculator out. Square root of 48, 6.928. Let's just call it 6.9. So A equals positive and negative 6.9. About, right? I should draw some like little wiggly lines there to show approximately equal. Again, we're talking about distance, so I'm not concerned about the negative part. So I would say that QK, I think is what we're looking for. QK equals 6.9.